then all of a sudden at time t equal to a, you switch it on to 1 from then on. Right? We call these type of functions step functions, right? 0, step up to 1. I call it UAT. So as a piecewise function, this is 0 if t is between 0 and a, and it jumps up to level 1 after a. The variable is t. Those are the step functions, right? 0, between 0, t is t, and then you jump up to 1, but after a. For values of t, the variable greater than or equal to t. So, what's the Laplace transform of, if that would be the non-homogeneous term of we will be interested in finding the Laplace transform of this function, right? It's a function of t, and the Laplace transform exists, and what is that equal to? E to the minus a times s divided by s. So this is a very important formula to remember. The Laplace transform of the step functions, like that, defined like that, UATs, are given by that equation. Now, in the context of what we were talking about, this type of functions, in the non-homogeneous term of the differential equation, another type of functions that might appear on the right-hand side of the differential equation as being part of the non-homogeneous term could be a function like this, right? So suppose that you suppose that you have a function clearly left of t, right? But you don't want to find, you pretty much if that's a function of t, I mean, whatever that is, we could compute the Laplace transform of that. But what we want to compute the Laplace transform of is of a function that at the beginning, from time t equal to 0 to time t equal to a, is 0. So 0. And then at time t equal to a, it jumps up to be this function, but shifted a units to the right. So okay. So you take and you shift this. And that's the ft up here. When you shift this, this is ft minus. Remember those from pre-calculus, right? And you shift horizontal. So you want a function that is 0 here, and then you switch it on to be current like this. Function. So this type of functions, this one, is really a function that is 0 if t is between 0 and a, comes up to be f at t minus a. If t, if the values of the variable t are greater than or equal to a. And what would be that function? Is a function that you get when you multiply the UA function you define over there by if the horizontal shift of the little function f a units to the right. So the graph of this is this. So if that would reflect what the non-homogeneous term on the right-hand side of the differential equation appears, we'll be interested in finding the Laplace transform of this type of functions. And what is that? What's the formula for that? Well, this is what it's e to the minus a times s times the Laplace transform of the function f. Very important formula. Number 2. So this, let me just put this as number 2 on this section, at the beginning of this section 9.4, and this would be number 1. And then the last formula that we want here is number 3. I'm gonna put it up here. It's gonna be when you have a periodic function to be in the non-homogeneous term. What does that mean? Periodic. It repeats itself, right? Mm-hmm. And that might be what the generator is doing, right? To the circuit. It's creating a voltage or is creating, setting the circuit by the battery generates some periodic thing into that circuit, right? So what if that the non-homogeneous, if the little f of t is periodic, function with period capital P positive, right? Well, for instance, if that would be the sine function, sine t, the period of the sine function is 2 pi, the P would be 2 pi. So we would like to have a formula to compute the Laplace transform of those periodic functions. Well, this is the formula. On the numerator, you have a definite integral from 0 to e, the period, e to the minus s times t, little f t, dt. And on the denominator, you get 1 minus e to the minus p times s. This is, let me just put it in a box again. Number 3. So that's the denominator, right? And those are the main 3 formulas at the beginning of this section 9.1, right? Formulas that you need, in a sense, you need to memorize. Number 1 for a step function UA, T. Number 2 for the horizontal shift of this function. 0 at the beginning. Okay. Yeah, formula number 2. And number 3, to compute the Laplace transform any periodic function with positive period, you get a ratio. The top of the ratio for that Laplace transform is a definite integral from 0 to p, and the denominator you get 1 minus e to the negative p times s. Any questions? So what we're going to do next is we're going to use these three formulas for the Laplace transforms to compute Laplace transforms of other functions of t, right? Piecewise functions of t. So let's start, let me just make some space here, keeping number 2. So, let's start with this. Suppose that they give you a function little f of t, which is 1 if t is between 0 and 2, goes back to 0, and then if t is between 0 and 2, 5, and this if t. Okay. And the problem in the exercise is asking us to find the Laplace transform. And the key to solve this problem, let me just make some space here. Remember this formula, we'll get back to it. The one we're going to use here in this exercise, because these are all constants, is number 1. And the key to find this Laplace transform using formula number 1 is to write down this in terms of UA functions. Of this type of function. And the result is the same. Right? Now, let me grab this thing. So here we have the vertical axis. So it starts being 1, like this. Then you bring it down to level 0, and it stays like this up to 5, and then it jumps up to level 2. So here is 1, here is 0, this is minus 2. This is the graph of this one. I mean, that would be 2 on the t-axis and